so that you can actually go and look them up yourself if you end up kind of doing some sort of numerics in your own mind. Okay. So this quick announcement. So office homework session video today. My office hours are after the lecture, and then Felipe will have office hours today in B115. It's a different room, so make sure you are there at 3 to 5 p.m. And then we did this last time, for exam, the office hours. I will do it remotely via like Zoom at between 8:30 to 9:30 on Sunday. So because you have exam on Saturday, so hopefully you'll have some time to study on Saturday evening. In the morning, I will do an office hour. Felipe also can have another additional office hour for the exam. But there are two options. You can keep it on Friday, but I figured that many of you might not be reading transport on Friday. So is there a preference between Friday and Sunday? So how many of you want Friday? How many of you want Sunday? So okay, so we'll do it Sunday. And then so let's cross this. And then the second thing is whether do you want it to be you want it to be remote or in person? And Felipe is open to doing both. So any preferences for remote? In person? All right, so more towards in person. So that's at 1:45. Yeah, so exam is at 1:45. So it's up to you. Any kind of comments for remote or what remote plus / in-person office hours for Felipe on Sunday? Mine will be remote. I mean that early morning, I don't want all of you. Some of you probably live far or something, so I just want to make sure I'm cognizant of that, and I'll post all the notes and everything. And I found that it's easy enough for me to navigate Zoom, so I can do in person also if there's a strong preference for that. But I figured it might be a little bit easier for students who probably live far to do remote. Any thoughts on? So what do you want? So Felipe's office has virtual. Anybody really strongly prefers virtual? One. And then how many prefer in person? All right, so we will do in person. And then what Felipe can do is also give you a Zoom link, separate Zoom link, in case somebody wants to join, really like to ask questions. We can figure it out. But we'll have the option. We'll try to give you as much input as possible. Okay, so I will put this on the email and kind of like make sure you all have this information. So my office hours will be virtual from 8:30 to 9:30 on Sunday. 10:30 to 11:30, Felipe will do in person. We'll figure out a room, and if somebody really wants to still ask questions over Zoom, we'll figure out a way to give also a Zoom link for like 10-15 minutes. Somebody can join or at the end or something like that. Okay. Okay. Any questions for any of these announcements? Anything anybody wants to clarify? All good. All right. Okay. So there are two parts to the class today, and what I will do is I'll start with the more kind of like general part, which is this is not going to be part of your exam, what I'm going to cover today. So just want to kind of briefly, so two parts. In the first part, probably is 15 to 20 minutes. I just want to mention what different numerical techniques are. Okay, so you will likely be using numerical techniques to solve transport problems in your research. And I just want you to be aware of different tools and what goes behind them. We will obviously not be able to cover any of that in the course, but you will have terminology so that you can go and look them up yourself. And obviously, you are also welcome to come to talk to me if you have any questions about numerical stuff. Okay, so let's typically just let me discuss about the different numerical methods in transport phenomena. Okay, so numerical methods in transport phenomena. And then we will do the review after that. Okay. So and I want to emphasize that from my experience, as sitting on committee meetings, sitting in prelim exams and so on, and talking to a lot of students and postdocs, students kind of don't appreciate that there are two kinds of numerical methods. One is that you directly solve an equation, which is direct numerical simulations. Okay, direct numerical simulations. So what this says is you will not simplify the equations even a little bit. You will just take the governing equations. Maybe you will simplify by saying it's steady, or axis symmetric, but that's about it. You will just say, these are my equations, 5 or 6 of them, and I will solve them. And from my experience, I've seen students really gravitate towards direct numerical simulations. And it is good that it may be needed in some scenarios, but there is the other side, which is basically reduced order modeling. Okay. And I really want to emphasize that from this course, I hope you have seen reduced order modeling. How you can first simplify the governing equations and not just like on the surface level, really think about different magnitudes of different terms, scaling analysis, really like, and then solve the problem. Okay. And then solve the problem. So I just want to emphasize that whenever you are doing any problem and come across in your research, this is always an option. Direct numerical simulation is always an option, but it may not always be a feasible option. You may have such difficult equations to solve, so non-linear, so stiff equations that you just cannot solve them. And students come, they have spent 3 or 4 months, 5 months trying to put something in console, trying to get it to converge. It just takes a long while, and then it just doesn't kind of, give them that information that they're looking for. So always remember that, yes, that is there, but you can always first try to simplify your equations to a reduced order model. Okay, so what kind of techniques have we learned in the course? So for instance, you can try to do 2D to 1D analysis. You can try to convert 2D to 1D by integrating out a direction, by averaging out something, right? Or you can use sort of dimension scaling analysis or order of magnitude analysis to drop terms. Analysis to drop some terms. So, and then we have also discussed some of the other things which you don't have to necessarily do them, but you can always further simplify the equations by trying to combine, kind of using something like similarity, perturbation, and so on. So those are always also the options, and you don't have to use all of them, right? Even if you use sometimes a simple approximation, that will greatly simplify your numerical, okay? And that can really help you simplify the problem. Okay, so that's the first step. I just want to make sure that you remember that whenever you're trying to solve a problem, transport phenomena, if something you can learn from this class is governing equation and boundary condition. But when you solve it, before solving it, we try to simplify our governing equations and boundary conditions, right? So that simplification step, don't forget that. So make sure whenever you're trying to do anything numerical, there is that option. It may not work out, in which cases go ahead and solve the full problem, but always try to see if you can simplify it. Okay, so that's step number one. That don't forget that. The second thing, I just want to kind of give an example of how you can learn to self-consistently do boundary conditions and example. So how to use what you learn in the course. Okay, so I will give you a simple example, and I want you to come up with a solution which you will try to tell me for boundary conditions. Okay, so in numerical simulations, boundary conditions in numerical simulations. So let's imagine you have some sort of a cylindrical surface here. Okay. And you're trying to just do diffusion, simple diffusion. You want to find this has some flux here, flux J. Okay. And by the way, this is again not a part of your course. I'm just trying to show you some ideas of how to think about numerical simulations. Okay. A and del square C is equal to 0, steady system. Okay. And you have a n dot grad C is equal to J naught J by D. And then far away, the cylindrical system, let's say R and some theta direction. What I want to basically make you think about is now I have this setup. Imagine there is an analytical solution for this, but let's say I did not kind of know the solution and I want to numerically solve this problem. Okay. So numerically solving the problem, how will you do infinity condition? So when you're trying to solve something numerically, what you try to do is you try to distribute that region into some sort of small volume elements, right? So let's say you make a domain size. Okay. So you create a volume in your region of interest. Okay, and then we'll discuss a little bit more detail later down. And let me first maybe just move them on the side. So you created this volume, let's say, but you don't have infinity, right? You cannot create an infinite volume in your simulation. I'm just giving you an example. So how will you try to create this volume? What can you do to make it like? Any thoughts? So like what can you do to make it like infinity? Right? So that's one thing. So you make it 100 times R, 10 times R, 50 times R. And you go and do this in numerics, and it turns out that the answer still does not align with the infinity answer. Right. So great. So such one suggestion was make it 100 times, one was 50 times. Now the suggestion is keep increasing the size until you start to get some sort of a tolerance value, right? So great. So all of these are good suggestions, but obviously it means that you need to know the solution beforehand. And sometimes you will not know the solution, right? The problem is because if you don't, let's say this is the problem you did know a solution for. In this case, you can, for instance, like find it analytically or integrate it out. But in this case, you may have a system where you don't know the solution, right? So how do you set an infinity boundary condition? And it's very common. I've seen this over and over again. So what you basically try to do, is let me try to give you an example of this. Okay. So if I'm sitting here, let's say you made this 50 times A. I'm just giving you an example, right? Now, when you're sitting here, do you see what the radius is or do you not see? For you, it looks very small, right? And basically that is called the point source. So basically you don't see the shape of the object, but you can imagine it. You don't really see what the shape is in detail because you are so far away, right? So the far away boundary condition can come from a point source solution. So for instance, if you make it half as flux, you don't make the flux to be full, you just make it half of the flux. So then you can say, well, if I'm sitting far away, I don't really see whether it's half or full. I just know that the total amount of mass coming out is just J times the half of the circumference, right? I don't see the full flux. And I'll forget so far away that it goes to the sheet effects. So what I'm trying to say is basically when you go towards infinity, remember that there is something known as point source solutions. And for all problems, you can find them, fluid mechanics, point source solutions, which can help you set the boundary condition. Okay. So in the course, and you can look them up in the book, and we have done in the class, we have called them point source solutions, but these are very easy to look up in the book and incorporate it in your simulations. Very easy to do that. And that can help you sort of, like really improve your simulation, and you will start to find that like you can essentially like get much more better accuracy by remembering that there is something like this in your system. Okay? Does it make sense? Okay. So when you're thinking of boundary condition, you may not have infinity. So you want to kind of represent it like that. In which case, just kind of try to remember some of the things we have discussed in the class of how you can use them to set the boundary. And setting this is very important. So the first step is simplify your governing equations, right? Like kind of simplify them. But when you're also setting boundary conditions, don't forget that some of the things that we have discussed in the class can be used. All right, now the third step is, so you simplified it, and you couldn't simplify it, and then maybe whatever you can self-consistently you have done, now the boundary conditions and the governing conditions, now how to solve them, right? So how to solve. So after simplifying governing equations and boundary conditions, how to solve. Okay. So here, I just want to kind of mention some of the different approaches that you can think about depending on the complexity of the problem. So different packages. One is called COMSOL, obviously, which many of you might have heard. One is called OpenFOAM. How many of you have heard about COMSOL? How many of you have heard about OpenFOAM? Not many. So there is a difference, and that's what I want to specify. So COMSOL is a finite element based method, and OpenFOAM is a finite volume based method. Okay. Finite volume based method. All right. There are some, I think there is something called free FEM or something like that, which is just like an open source FEM, which is the finite element method package. If you want to kind of look into those, then there are always other kinds of now packages coming up, which is in like MATLAB. There is something called PDEPE solver. PDEPE, there's Python, and there's a new open source language called Julia, which all three of them have very good, very good differential equation solvers. Okay. All right. So what basically, and there is a slight difference. Okay. The difference is in these OpenFOAM, free FEM, and all that. They rely a lot on sort of like complex meshing. Okay, so meshing basically is creating. So they use complex meshing algorithms. Complex meshing algorithms. And what is meshing? Meshing really is the volume, like we were discussing this volume. You start to divide them into different shapes like cuboidals and like, so on. So divide, this is essentially dividing the volume in elements, in small elements. So in my PhD, I had remembered I had used OpenFOAM for a project, and it was a headache to just mesh. This meshing was like so difficult. You have to go and manually do everything, and there are professionals who just do meshing for their life. Like their entire life, they're just trying to do meshing. COMSOL has very advanced, for instance, meshing algorithms, like where it tries to mesh automatically, so you're not given that much flexibility. So sometimes it will work, sometimes it's just maybe too simple for difficult problems like turbulence and so on. You have to be very carefully meshing some of these volumes. So, but just remember that these things rely on meshing. In some of these PDEPs and partial differential equation solvers, I'm not talking about partial differential solvers, they don't even ask you for meshing. Okay, so you basically they may ask you some of these solvers will just give you an answer. Just give you an answer, you put the boundary conditions and stuff. So this is automatically done behind the scenes. And so they again take the results of the like kind of always make sure you're testing them out for trusting any of these results in either of the scenarios. So you will not be asked to mesh here, okay? Asked to mesh. Finally, I do want to mention this because it has gained a lot of traction in this transport community. There is a method called physics-informed neural networks. And the person who discovered this is actually a professor in applied mathematics at Boulder. It's a very, very popular technique now. So if you are kind of interested, you can read them about this. They're essentially a differential equation solver. The idea is that a lot of neural network algorithms need the data. Okay. So what you say is, well, we'll first generate the data using direct numerical simulations. I'll go into the hard part. I'll train a solver, and then the solver will be able to kind of give you the answer faster. So that's the usual neural network. What physics informed neural network says is, well, I already have the equations. So why don't I generate the data from the equations themselves? So for this method, you don't need to supply any training data set. Your equations are your training data set. So it directly gives you an answer and becomes like a differential equation solver. And you can use them in some cases. We have used it in micro, we have tried them, they work. But we haven't currently kind of explored them enough. So kind of, you kind of put some of the problems we're interested in, but you may be interested in some of the design problems, especially for like optimizing something and so on. There are packages in Python which kind of do the physics informed neural networks. Okay. So these are kind of the what is out there in terms of methods. Okay. So any questions about different packages and how to approach them? Any questions, or somebody wants to ask about something else you might have heard or anything like that? All good? Okay. So next 10 minutes, what I will do is I'll give you an example of what goes behind some of these calculations. Okay. A small example like that, but just a small example. So let's see. Let's take a quick example. Example of numerical solution to PDEs. Okay, so how would you solve a PDE like this? So we have a PDE del C by del T, dA del square C by del X square. I hope when you go out from this class, you remember that there was something called FFT, which we used to solve this, or for a finite domain or for an infinite domain, we use similarity transform. So this is all dimensionless. So don't worry about like kind of any of the units right now. This is just to show you an example. And so you have been given two boundary conditions. So the domain is X between 0 to 1. And CA is 0, and then this is actually 0 to solve. Okay. So now numerically, I want to kind of have you kind of come up with ideas. Numerically, we know this. So how do you think we should solve this problem? Numerically, just give me ideas, whatever comes to mind. What do you think is the first step we can do to start making progress to reduce the complexity? It's a partial differential equation, right? So there is no general technique right now that you are aware of. So how do you even start this? Any thoughts? So that's a great idea. So think of a numerical solution. We are currently not trying to do anything which is more sort of reducing the complexity. So good question, good comment. So what we can simplify it further. Let's say this is the simplest equation and the boundary conditions that we have arrived at. We had a very difficult problem that we have reduced to this. And now you want to numerically solve this. So it's a partial differential equation. What's the next level of complexity below partial differential equation? Ordinary differential. Okay, so that's the first thing. Is you will first, we'll try to make PDEs into ODEs. In class, we learned that how to do that. So similarity solution was one of them. To prime for the transform was one of them, where we kind of remove one of the dependency and make it ODE. But now we want to do that numerically. Okay, so how do you do that numerically? Is you say, well, I want to go from X from 0 to 1. Instead of doing that, I will divide my domain into several points. Okay, so 0 to 1, instead of solving every point, I will say I will solve at, let's say, 100 points. This is xi, for instance. Okay, where I goes from, let's say, you can divide, you can decide this of how you want to put this. I could be going from 1, 2, 3 to, let's say, 100, 500, n, whatever number n comes out to. This is simplest form of measure. You do this at a much difficult, much more complex three-dimensional space in console or open form. But I'm just trying to show you what goes behind it. Okay. That's the first step. Now, the problem is that, so would you, I hope you can all see that this partial differential equation will now apply at each point, right? Basically, the partial differential equation will apply at each point. So how do I make further progress? Is that I will try to say the derivative, which is del square k over del x square at a location xi. So now from CA of x comma t, I have gone to CA of xi comma t. Okay, so this is how I have transformed it. And the way you kind of try to do this is you start to use something like, Taylor series expansion. So what you argue is C of I plus 1, and we will, for now simplicity, let's assume all these are equally spaced, delta x, delta x, delta x, and so on. Okay, so this is how you start to see Taylor series expansion. And what we are trying to show here is that now I can start to represent my del Ci by del x as algebraic formula for C I and Ci. So when you add them, and you can just do this, pretty easy to do. So when you add them, you will get essentially, it's pretty easy to see, del Ci by del x, xi is Ci plus 1 minus Ci minus 1, or sorry, subtract them, you will get this out, and there's some errors depending on the delta x. So this is some errors. Okay, so these are just errors which we have not, because we have not done all the Taylor series. So these are errors that remain. So the point is, I can kind of find first order, second order terms, right? And now I can substitute this, and I can substitute this and put this back here, right? So now I will get an ordinary differential equation in terms of Ci and Ci minus 1, Ci plus 1, so on. Essentially, instead of one partial differential equation, I get a series of ordinary differential equations, right? So from one PDE to substitute. So from one PDE, you get a series of ODEs. Okay. And I presume in kinetics, or at least in thermo, you must have done ODEs even in this semester, and in time, if you want to integrate in time, is the Runge-Kutta schemes and different time algorithms. Even that, if you want to learn, you can learn, but like basically it's pretty easy to do them. And so you can convert them into series of ODEs. But remember, we also have boundary conditions. And so boundary conditions add another layer. And so those are algebraic equations. So plus you get some algebraic equations. So you can convert these derivatives here also in algebraic equations and so on. And so this becomes essentially like a system of DAEs, or differential algebraic equations that you can easily solve. You can also convert them into ODEs. There are different methods after this point, but I just wanted to show you that whenever you are solving COMSOL, this is what is all happening in the background that you don't see. They're trying to convert your PDE into many volume elements, converts that into ODEs, integrates it in time or space, and gives you the answer. Okay. And whenever it fails to do that, or whenever there are some solutions that show instability, If you are struggling to kind of convert the solution because your division of volume may not be fine, or the problem may be very numerically difficult to, because this is a linear problem, easy to do. But you have you have multiple variables, sometimes they're interacting with each other. So always kind of try to question the result of any numerical solution and try to kind of benchmark them with simpler problems to get confidence in your solution. Okay. So this is a mechanism. We didn't have time to cover this, but like in general, you can slowly build it up. I have actually built codes myself. It doesn't take too much time. You can at least do 2 time dependent problems pretty easily. So like they are like linear problems, you can slowly go and build them up, and you can start to see something interesting, things that we are not able to do analytically. So yeah, and in general, if you encounter something like this in your research, just remember some of the basics, and I'm obviously always available to chat. Okay. All right. So any questions on this numerical scheme? In prior attempts, I used to actually go through a code, but I just decided because we have not had time to discuss them in the class, it doesn't add as much value. But if you're interested in any kind of codes or simple problems, don't hesitate to reach out to us. We have several of them. Simple problems we can easily help you with. Any questions about numerical stuff before we go to the review of the class, third part especially? Anything? All good? All right, so let's pause here. So it's 12:37. We'll start at 12:42, and then we'll review the entire course, briefly the first 2 parts, and then the third part in detail. Yes. Right.
I'm confused. I understand the analysis.
Right.
And the answer is
Right.
neat, but then when I compare it to the table,
Yes.
there's a difference. It
Right.
says it should be different to one.
Yeah. So the reason there's a difference is because remember, these are all derived for assuming a stationary solid. There was the no slip condition that meant the velocity was 0. But here there's a slip, kind of like a fluid intercourse. The solid is also moving.
Because I thought like if you change to a different reference frame where the plate is stationary and the velocity is just u/2.
Yeah, so you will not, I think so it's a great question. I think you will probably start to you will not be able to get the self consistency in that case. So great question. And I mean, it's a good kind of angle of thinking. But I think what I'm trying to say is basically if you were to change your equations, because of the fact that there is a u del u by del x, you just change the reference frame. There's inertia now. That's why there is a boundary there. You will not be able to get the same sort of. So linear problems you can easily do change, and everything works out. This is a non-linear equation set. So if you define a new u, let's say u prime as u minus u by 2, you start to see like a term that is sort of left over, and your governing equations will not be significant.
So it's like I can treat as slip because the plate is also moving.
Yeah. So it's like a slip condition in a way. Like, I mean, it's a no slip in the sense that the fluid also moves with the plate,
but it's moving
with the velocity. So but does it make sense what I'm saying? Just to clarify, if you were to define rho, and if I was to define x prime minus 2 by 2, then I do get a rho. This term, you cannot say full back. It's a reference thing. It's like. Of course.
All right, let's get started. So we have about 40 minutes remaining for the lecture. So I will try to cover like, maybe 5 to 10 minutes each for part one and part two, and then spend most of the time in part three, which is obviously the course that will come in your exam. So in part one, essentially, remember that the focus essentially for us was diffusion and conduction. And I want to kind of remind you that we had discussed liquid phase diffusion, which is what we have done primarily in the class. But we also discussed gas phase diffusion. Where was this mass average velocity, molar average velocity, and so on became common. So some of you end up working on any gas phase diffusion problems, whether you are trying to, capture carbon through like a porous electrode with gas diffusion, or you're trying to do electrochemical systems where there is generation of gas phase through some electrodes, or you have some catalysis problems where you have gaseous diffusion. Remember that the transport equations are slightly more complicated, but the liquid phase and conduction is what we focus mostly on. We discussed the problems like 1D steady problems. So we started discussing like diffusion reaction problems, purely diffusion problems, how to define fluxes. And the key thing that you learned in this class was interfacial balance. Okay, so this is a very important concept that you can remember going beyond this class, is that most of the times in your research you will be working across interfaces, almost always. Biological transport phenomena, it will be across an interface. Anything that I can think of in practical setting you will be doing, there will be likely an interface there. So interfacial phenomena, interfacial balance, don't forget that. And remember that interfacial balance is across any geometries. We did in planar geometries or simple geometries, but it can be an arbitrary geometry and you can still apply the formula. And so that's something that I would say it's an important thing that you can remember from the class. Then we went to discuss things like 1D unsteady, 2D to 1D. And here we invoke things like similarity solution or averaging out a dimension. While in most likely scenarios, you will not necessarily be using them directly in your research problems because these are very idealized systems. Remember that these can give you a good check. Okay, so sometimes you can reduce the complexity of the problem by making assumptions, and finding the solutions can give you confidence in the numerical solution, or may just give you an idea of what's going on in the system, right? Just kind of give you a better understanding of what's going on. Finally, then we discussed the two more important ones, I would say, for PD solving linear problems. We discussed the FFT, or the finite Fourier transform method. And I took this class 10 years back, And I've used this chapter for finite Fourier transform, like, like at least 100 times, because if you have to look for a differential equation for a linear problem, you have to kind of go and look at FFT. To give you an idea, I'm not like making this up. I was on a call with a collaborator like this early this week, and they realized that they were trying to do this COMSOL modeling and all that, but the solution was in the book. Because it's in the chapter. So like if you find a linear problem, I'm not saying it's going to work every time, but just remember that there is something out there that you can just take a look, and can solve you like all this headache of solving. The solution was right there, like it was given in the book. So and I also refer to it, by the way. I mean I keep referring to the book again and again, partly because my research is kind of important. For that it's important, but in general it's a useful text to see how to solve differential equations. And so it's just remember that it's always there. And then the second method is perturbation analysis. And there is a small, you find a small parameter epsilon, and you try to expand in the orders of epsilon, right? So theta is equal to theta naught epsilon theta 1 plus epsilon theta square 2 plus so on. Okay, so that's what you do. I now have, because we have done the boundary layer analysis, there is this other side, which is basically that we kind of ignored when we were talking about it. It's called this. So what we did initially was singular perturbation. So a regular perturbation. So regular perturbation means that the difference between having the small parameter and not having the small parameter is not drastic. So for instance, having a small reaction and no reaction, not that different, similar style. But having a small viscosity and zero viscosity was a big difference. Remember that when we had no viscosity, we were just getting nonsensical answers, that there was no drag, and so on. And then when you add this boundary layer idea, that there is a boundary layer, so that is actually related to perturbation analysis. So the other arm that now you have seen is called singular perturbation. And that's basically boundary layer analysis that I'll discuss a little bit more in detail. But why I bring this up is because this is something that one of my PhD students is actually kind of working on, but not in terms of fluid flow or anything like that. Nathan is working on using kind of these ideas for redox reactions with electrical double layers. And we learned that it is very similar to like a boundary layer analysis. And so we were able to kind of make progress in kind of understanding physical phenomena. So remember that like this thing, but the idea is while we read it in terms of boundary layers, fluid flow and so on, the idea is that if you have a small value, but that small value makes all the difference, right? So if that is the case, you may be able to kind of see that it's important to kind of use some sort of this idea. Okay, so I'm just trying to show you how to use this course more broadly beyond the topics that we have discussed. Is that if you see a small parameter that is, and the answer is very different, you anticipate it to be very different, then there might be some sort of a singular perturbation analysis that you can do, okay, which is like a boundary layer analysis. All right. So this was kind of the end of part one. So essentially in part one, what we said was we'll have no convection. So we did not discuss any convection. So we ignored convection altogether. Ignored background convection. We derived conservation laws. We discussed interfacial balance boundary condition, and we then discussed different kind of methods to solve the problem. Okay, so that was what we discussed in part one. In part two, we started adding more complexities into the system by saying, now we want to add flow, but adding flow to the heat and mass transfer problem right away is difficult. So then we started basically focusing on the fluid flow by its own first. So fluid flow was where we started this part. And I just want to emphasize a couple of things so that because that is also relevant for your part three and also part of your part three in a way, is that in fluid flow, we obviously derived the equations. So we derived equations. Conservation equations, boundary conditions, and so on. But I want to emphasize basically the different kinds of things we discussed. Unidirectional flow, right? So remember we discussed this dp by dx is equal to mu del square vx by del dy square, and then this was a constant, and this is, we are talking about like a flow within a plate. Okay, this is something you did in your homework problem. You had a slip of the plate, so you added another layer and so on, boundary conditions and so on. So we discussed unidirectional flows. Remember that we discussed this was under the fully developed, sort of fully developed condition. Okay. So what is this fully developed condition? And I never got a chance to explain this because we hadn't done this before. Fully developed essentially means your boundary layers have developed for the momentum part. So just want to clarify, fully developed momentum means that the momentum boundary layers have merged and have gone through the entire system. So we kind of focus only on this. We essentially solve for this region. Okay. And then it's fine because you can just ignore that. So that was the first thing we discussed. That is very important kind of for you to think about how we think of flow, and even this goes as a feeding kind of, the velocity feeds into your boundary layer problems for concentration and mass, as we will discuss in a second. Next, we discuss nearly unidirectional flow. Okay. And here essentially what happens is the classic problem is always this converging channel. What we found was that, remember that the governing equation looks same, but it is not exactly the same. It's mu del square Vx by del y square. So instead of a d, there is a del square because Vx is also a function of x. And this is not constant, but just like some value, right? So this is not constant. Okay. So we found that the answers look very similar when you integrate out. The velocity looks very similar and so on. Just that we cannot integrate fully because dp by dx is not constant in x. So what we did was we found an invariant, and then we kind of made progress. So we found an invariant. To kind of focus on that. And here we also had the air hockey problem and so on. So part of the exam, and so those are the things we discussed at this point. But the equations was kind of mostly around this, similar ideas. Then we discussed after this we discussed the creeping flows. And this is something you're even doing in your homework now, like still kind of recalling some of the things we discussed. Del 4 psi is equal to 0 or E4 psi is equal to 0, right? So in creeping flows, when a large number is smaller than 1, we discuss this drag around a sphere, and we derive this condition, and you kind of went through this whole exercise in your homework to find what the flow profile will look like. That was creeping flows. So here the point was we derived the full conditions, and then we had simplified equations for each different parts, right? Then we had final part we discussed in part 2 was potential flow. And there it was del square psi is equal to 0 or E square psi is equal to 0, or you can use del square phi equal to 0, or phi was the potential. So either approach worked, and we used two different approaches. In the class, I think we did using the psi approach. In your homework, you did using the phi approach or something like that, and you got kind of same answers. Essentially, you can use either approach. It works out fine. The answer is still the same. So this was kind of different kinds of flows we discussed here. One thing that came out to be very important in this part was how to calculate forces. So you can solve this problem, but don't forget that to calculate force, we use the SNDS, or stress vector times ds, and that you cannot directly integrate in curvilinear coordinates. So please don't forget that. If you end up working on a colloidal problem, you have a spherical particle, you cannot just directly integrate. You have to first convert into Ex, Ey, Ez, then integrate out because curvilinear coordinates are changing the direction. And then we also discussed torque, obviously, that it was R cross ds. So we discussed both the forces and torques, but primarily forces. That was the focus of the of the course. Okay. So any questions for part 2? Anything anybody wants to discuss before we move on to part 3? Anything that was confusing at the time is still confusing? Happy to. Yes. It's a T, torque. So yeah, this is torque, total torque. I think the book uses sometimes a G vector, and I might have used G vector as well at times. So this is this. And Sn, remember, was a stress vector, right? So Sn was the stress vector. And it calculated using n dot sigma, right? N dot sigma. All right. Any questions? Other questions? All right. So let's start to now go towards part 3, which is I'll go more slowly and we'll discuss exactly if you want to stop me at any point, anything that is confusing. Don't hesitate. All right. So when we came to part 3, in part 2 we had learned that this solution gives the drag force to be 0, right? Here the drag force or the force was only, it was still SNDS, but because there was no viscosity, it became basically minus PNDS. And whenever you integrated the pressure force, you basically got out the answer to be 0. And that was the D'Alembert's paradox. So that's where we ended the part 2, that we want to focus on high Reynolds number flows. So this is Reynolds number literally infinity, but this does not get the answer right, because clearly if I'm flowing so fast, I should expect a drag. Like we just physically see, put a particle, you're flowing with very high velocity, the particle should experience some drag, but it seems to not be the case from theory. So what's going on? And that's where the idea of boundary layers came in, and that's where we started the course, is that we basically said, okay, what we will do is we will think about flowing here, but we'll say in the inner region. So we defined y as perpendicular to the surface, x as parallel, and then we zoomed in, and what we found was that if x is parallel, y is perpendicular, then we start to get this. We argued that we will get this momentum boundary layer, and for simplicity now I'll call it delta m, because we know there are other deltas written down. So delta m of x boundary layer. Here in this portion, viscosity is matter. So viscosity is important. Mu is important. Outside, I still have del square phi equal to 0, right? So that is how we kind of started sort of thinking about this problem, was that this is what we can do. Obviously, we can't do the full order of magnitude analysis, but we did the full order of magnitude analysis in the class, and we derived the boundary layer equation. So from Navier-Stokes equation, to inner region, only focusing on the inner part, our equations were Vx del Vx by del x plus Vy del Vx by del y is equal to u du by dx plus nu del square Vx by del y square. Okay, so this was the case we were discussing, where the outer region comes through here. Outer region Vx x comma 0 is equal to u. From the outer region, we calculate the velocity, which is a function of x. We put this value here, and we get this boundary layer equation, right? So this was the full equation, which we said Blasch's solved to get the kind of drag coefficient. Sorry, not this form. We'll simplify it further, but this was kind of the boundary layer equation. So sometimes students forget this, but just remember this is similar to your unidirectional and nearly unidirectional or creeping flow equation. Whenever you see a boundary layer, the flow will be like this. Basically, that's the idea. Okay. Now, for the yes, please go ahead. Oh Oh, so that's the for the u du by dx. So this portion essentially comes from the outer region. So that portion of the form equation comes from the outer region. Yes.
So if that comes from the outer region, you don't have to solve the outer region, so.
So you have to solve the outer region to get the u and then feed that u into the equation.
Okay.
So because you will not know u until you solve the outer region. So maybe let me maybe back. Just give me 1 second more. So why is that? So remember I have written Vx comma x comma 0. So I'm calculating a parallel velocity on the surface. But remember when you're doing the outer region, the no slip does not apply because we have fewer the small orders. That's a slip that you're calculating. But we're saying that's not really a slip. It's just we are not looking fine enough, and then we use that as a way to get to the fine part. So that's how that connects. Yes, go on.
This outer region going to have the same velocity as the outer region?
So good question. So that's slightly different in the sense that we are now currently looking for flow around a particle. So don't try to so that is flow within a channel. So good question. So what Noah is asking is how would that change to something like this portion right here, which I sketched out where the two boundary layers are merging. So remember that the problem we are talking about for drag there is flow around something. For a flow within the system, this essentially this sparse portion is assumed to be constant. It's a different setup. Like we are not talking about two boundary layer problem. So merging of boundary layer and so on. They're related, but there are some other details that we have not discussed. So don't get confused. Whenever you're thinking of this for now, while they're related, and you can use these equations also for the channel flow in some form, just remember that this is more for flow around. Just for around a particle, just to keep things easy. Okay. Now, what I really want to make sure all of you are able to for your exam and for your learning is essentially be able to understand how to do order of magnitude analysis. Okay, so let's do that quickly so that you all remember that. So here we so for a flat plate, by the way, for a flat plate, it turns out that u is simply u naught. It does not change. And so your boundary layer equations becomes Vx del Vx by del x plus Vy del Vx by del y is equal to nu del square Vx by del y square. And we also obviously have the continuity equation. Okay. So now this is something that I would suggest if some students get confused and some students prefer to do it on both equations, you can do it. But for your exam and for in general, just sometimes sanity check, you can always remember that you can take the x direction, which is along the surface. So remember, this is along the surface. And say this will be balanced by perpendicular to the surface. Okay, so you can always write it like this. Kind of like diffusion, but it's not really diffusion, shear stress along because the first two terms are the same scale because of the continuity equation. So I'm doing a shortcut essentially here, just trying to say that you can directly write this. Why? Because now this allows me to say Vx scales as u naught, x scales as delta x scales as x, delta y scales as delta m of x. And when you substitute this, you get out delta m of x is nu x by u naught. Nu x by u naught. That's what you get out. So, okay, so just remember this kind of trick, and I will do this again and again in the just going forward. The scaling analysis can help you sort of simplify some of the equations a bit easier. That I'll take the x part of the convection and balance it with the y part. The kind of the diffusion, in this case, it's the momentum diffusion, nu term. Okay? Yes. Yes, absolutely. So why I got rid of the other term is because I'm saying that this portion and this portion would be on the same order because of this. And I don't carry the factor 2. So think of it like this, that convection in the x direction of momentum is balancing the diffusion of momentum in the y direction. Okay? And I will show this for species and temperature also this works, energy also it works. Just easier to kind of do it this way. You can, by the way, you can also do it on both problems, absolutely. That's fine, that's what we did in the class. If you want to just kind of simplify a little bit, this is just makes it life a bit easier, okay? I mean, you still have to scale everything correctly, but this is a good starting point to kind of not do all the different geometries and so on. This is a good easiest.
So for boundary problem, you say you zoom in and so you use criterion coordinates.
Yes,
So every time you have a boundary problem, you switch it.
you can do that. Absolutely. Yeah. Any boundary layer problem, you can like a high Reynolds number. So good question. So remember the Reynolds number is high here. So momentum boundary layer is small, like this is what we have discussed, like this, it will be small. And so yes, whenever your high Reynolds number or very high Peckley number, that means that the boundary layer thickness is much smaller, the momentum or the concentration boundary layer thickness or the temperature boundary layer thickness is much smaller than the dimension. So you can always use Cartesian coordinates, absolutely. Not there, that is never going to be a problem. But you have to have these conditions, by the way. If you don't have large Peckley number, then you cannot use them, or large Reynolds number, you cannot use them. Okay, so remember that, and I'll clarify that once I go to the next part of the combined heat and mass. Okay, so we have this. Any questions here? All good. Okay, so then we also discussed typically like that momentum boundary layer at the length scale L would be nu L by u naught. That's one thing. You can also scale wall stress, so you get mu del V x by del y and y equal to 0. So this becomes mu u naught by delta of m. We had a drag coefficient as fd by rho u naught square by 2 times w times L. Fd is mu u naught by delta m times and the length, this is the length of the plate and this is the width of the plate. Okay, the width of the plate. So and then by rho u square times like this. And once you do that, basically you can cancel this out, and what you get out is you get out to be CD to be Reynolds number to the power of minus half. Because this is essentially L times Reynolds number to the power of minus half. So you can kind of use Reynolds number definition to simplify this, and you can simplify this. Is not that takes a few minutes to just do it, but it will be easy to show. Okay. So does this make sense? Any questions on how to scale everything? So you get the wall stress by mu del V by del y. It's just, so I think we had spent a lot of time on this topic saying how to think about this number is that the wall stress has a viscosity in it, but it is the delta M also the viscosity, so it's the balance of viscosity and density, and like it's like a mixture. So in the sense, at the end of the day, shear stress is still diffusive, but the length scale or the sort of shear stress, this length scale is set by the balance of inertia and the inertia and shear stress. So delta M is the magic there. Okay? So the delta M is the magic which goes throughout and gives you this diffusion part. Okay. Yes.
So when do we use like a variable like x, and when do we use?
Very good question. Excellent question. So you will use X whenever there is a channel flow or a flat plate. Whenever there is flow around a particle, the length scale is only radius or length L or whatever, like the length, let's say it's like an ellipsoid or something. So whenever there is flow within like a channel, like or a flat plate, use X. Whenever there is like flow around something, just use R, whatever, like R radius, most obvious. Okay. Any other questions? Great question, by the way. Any other questions? Yes. Yeah. So were you asking just about this one particular geometry, or general was that? But Philippe also wanted to clarify that if you let's say want to find the drag force, that is the total force. In that case, use length to be X to be length, right? But if you're trying to find the local value for Nusselt's number, Sherwood number, or in this case, local wall stress, just use the delta of that X. Okay. But for a flow around the object, it will always be just the radius. Make sense? So even within the flat plate or a channel, you can have two different One is for the drag force, just use the L, but for the local shear stress, use X. Make sense? Yes.
What is the
So basically, like we use this new X here, right? But then I am using L for kind of calculating here. So when you're trying to calculate total property, use L. But when you're trying to calculate a local property like a wall stress, use X. Okay, that's the point. So, and you will only use X, Z, and something like that when you have something like a channel flow or a flow along a flat plate. Okay. All good?
Sorry, just the drag coefficient is FT over
Rho unit square by 2 W times L. Yeah. Okay. All right. So let's carry on with the next portion. So this was chapter 9. Then we went to chapter 10, which was about so we discussed two problems here. So we discussed this. Okay, so this the flow was already developed. Flow is fully developed. Okay, and then we use the temperature of wall, and then we said there is delta T, T naught, and then we were trying to do the sort of solve the full problem. And in your homework, you had a similar problem where you had a falling film and the boundary layer was forming like here. This was air, and the flow was again fully developed. I believe it's like this here. Yeah, flow is like this. And you had for momentum. So in these problems in chapter 10, look, first it's like channel flow. So here, when I'm trying to calculate Sherwood number or Nusselt's number, I will be trying to use the local coordinate X. Okay, just want to make X or Z or whatever the coordinate is. That's point number one. Point number two is that the flow is fully developed. So you can use the unidirectional flow expression that we have discussed in part 2. Okay, so you don't need to know exactly all the details from your part 2, but you just need to know, like you did in your homework problems, how to set up a problem, right? You know, how to write governing equations and so on. You will not be asked to solve anything in detail. I just want to make sure, clarify that this is still a part 2, like we have done in homeworks. You can be asked to set up the problem, and you will see this in your practice exam as well. Like what are the governing equations for fluid flow, boundary conditions, and so on. Okay, but you will not be asked to kind of solve them in detail. Okay, just remember that. So now these are the two problems that you kind of remember this. This is homework 5, problem 3. By the way, here this drag coefficient was homework 5, problem 2, I believe. Sorry, problem 1 and problem 2. There were only two problems there. Problem 1 and problem 2. But remember that now I can just do this, and I want everybody to kind of make sure that you're following this. I can say this is my Z direction and this is my Y direction in a way, because it's near the developing region. I can just say, and I hope you can all agree to this, you will get basically Vz del T by del Y is equal to alpha del square T by del Y square. Okay, this was Sophie's question was, we are in the boundary layer, but which boundary layer? Temperature boundary layer. So I am now doing this Cartesian problem for the temperature problem. So please make sure it's clear. I did this, right? I'm sorry, this not del T by del Y, del T by del Z. So it's convection in the Z direction, the main direction. Convection in Z is balanced by diffusion in Y, and Y is not defined from the center like radial coordinates, defined from the surface. So Y is always defined from where the boundary layer is forming. Okay, so note the Y there. And here, the main difference essentially I want to highlight is you can do delta T is T wall minus T naught. You can do delta Y is to be delta T. The main thing is for Vz to scale, Vz is given by 2u into 1 minus r by r whole square. Okay. And when you scale this, essentially, when you put r to be r minus delta T here, what you get out is a u times delta T by r. So this is the important part. That the velocity near the wall we know is going to be close to zero, but it will be dependent on this ratio delta T by R. Why is this delta T by R coming here? Because this is no slip. No slip. So the velocity can have a scale of U or a scale of delta T by R, or the R here is the momentum boundary layer thickness, right? Okay. So I have a full supplementary video on trying to explain you all of these different relationships. So please make sure to check it out if it's confusing. Is that when there is no slip, like there is velocity is exactly zero, close to zero, then you use delta T, that moment, the thickness that you have interested in, and by the momentum boundary layer thickness. In this case, it's fully developed. So my momentum boundary layer thickness is R, right? I don't have any dependence. So get out of, you will get out of one third here in the answer. And finally, when you want to calculate Nusselt's number, just remember it's R by delta T. Okay, so that's all. So it's R by delta T. So once you scale delta T from that, you can get the Nusselt's number out. Okay. Any questions here? So that makes sense. So you can just directly write that equation and get this answer. Okay. Now let's do another problem which we were discussing, which you are doing right now in your homework as well. This is in chapter 11, is flow around a sphere. Okay. Like a heated sphere or something like that. So let's say this is T wall, flow is happening around the sphere. Okay. So there are different, and by the way, before I forget, this is all for Peclet number larger than 1. In which case delta T by R is smaller than 1. Okay. So when the Peclet number is large, you start to see a boundary layer, just like Reynolds number. When Reynolds number is large, you see a momentum boundary layer. When Peclet number is large, you see a temperature boundary layer or a concentration boundary layer. Okay. Now, so if I want everybody to participate. So if Peclet number is small, what should I expect my boundary layer to be? So there is no boundary layer in a way, right? There is no boundary layer because Peclet number is small. So it is the only thing you can do is you can say delta T will scale and the length of scale of R, right? So your Nusselt's number comes out to be R by delta T comes out to be 1. And so in your homework, you get this out to be 2 or something, right? In your Sherwood number to be 2. This is one of your homework problems. Regardless of Reynolds number, doesn't matter, right? If Peclet number is small, I'll just get a Nusselt's number to be 1, 2 or something like that, 5, whatever, right? Then if Peclet number is large, there are 2 cases. Whether Reynolds number is small or Reynolds number is large. Okay, by the way, we are talking about fluid solid interface with no slip. With no slip. A fluid solid interface with no slip. What you're doing in your homework problem is fluid interface with slip. So just remember that whatever I'm discussing now is not necessarily going to apply for your homework problems, and there are tables in the book that can help you in exams and so on to think about it. But just to kind of remember what the discussion we are doing is sort of like for these scenarios. For Reynolds number, small is not that complicated. Basically, we'll say again, now we have a boundary layer here, delta T. I'll define X and Y. I'll say Vx del T by del X is similar to alpha del square T by del Y square. Okay, X along the surface. So now Vx is an important problem. What will be Vx here? It'll be, and the velocity here is U. It'll be U times, note this, delta T by momentum boundary layer thickness. If the Reynolds number is small, there is no momentum boundary layer thickness. So what we get is R. Great. Okay. So that's all. And delta T is T wall minus T naught. And now to answer the question, now delta X cannot be local because it's a flow around a particle. So I'll just say delta X is R, delta Y is delta T. Okay. So you can get the answers from here. You will be able to get the answers from here that Nusselt's number here you will get out to be Peclet to the 1/3. Okay, so you can verify this. So this is very important for, I would say, for your exam, just spend time on this to understand this. Okay. Now here, there are further two cases, Prandtl number small and Prandtl number large. This is the one that is more kind of relevant for, physical systems. Next one. The equation remains the same. All the other estimates also remain the same. The difference is now my Reynolds number is large. So my Vx will be U times delta T by delta M, because now I also have a boundary layer momentum because the Reynolds number is large. And delta M is R radius times Reynolds number to the power of -1. This is from the momentum boundary layer portion. Okay. And then you can substitute and get all the answers. Okay. You substitute this and get all the answers. For Prandtl number smaller than 1, what will happen is I will say my momentum boundary layer thickness is smaller than the temperature one. So I use scale velocity Vx as du. So that's all. Everything else remains the same. You can get different tabulations and that's yes, please.
That is fluid.
Yeah. So
That
yeah. So for fluid, yeah, good, great question. For fluid, when Peclet number is small, we know Nusselt's number would be simply still be 1 or something like that, right? It's not going to change. When Reynolds number is large, for a fluid interface, what do we think is the velocity scale? Is there any no slip? No, right? So you simply have, for all the cases, you simply have the same answer. Vx is U, delta X is R, delta Y is delta T. Simply that. And so there you always get Nusselt's number to be Peclet to the power of half. Peclet to the power of half. Okay, that's it. There's nothing else. The velocity Vx is always U because there is no slip. No slip does not apply. So I don't have to worry about that. I only have to worry about when I have a no slip condition in the velocity is exactly 0, but I can't use exactly 0 because it's close to 0. But how close? U delta T by R or U delta T by delta M or simply U. So these are the different scales. Okay. So that is what the homework is trying to kind of show you, is that you will just always get the same answer in this fluid interface, and the table will reinforce that. Okay. So we are out of time for kind of going to chapter 15. So what I will do is I'll create a short brief video to kind of explain it. Yes, do you have a question? Yeah, let me just check. I should have it. Does anybody have the homework? I think it's still table 11-2 and 11-3. But can anybody confirm this? Yeah. It's these two, yeah. So these, please look up this in Bean, and these can kind of really help you understand the different parts. Okay. So yes, Rajesh.
This program for large Peclet number, we had
Right. For the large Peclet number, there is a clear definition, but we don't count in the order management analysis. That's all.
So when we write the equation, when we are not maintaining a calculation, and Peclet number is much less than 1.
Right.
To keep the like for program, you should have
Yeah, you should keep it. That so I think I'd answer this question in a boundary value problem because you don't have to have that, because you have inner surface and outer surface, so you don't necessarily need a either one. Even numerically. By the way, before I forget, so I will create a brief video for chapter 15 for you to review. I think that's better than rushing it anything. So I'll create a brief video for chapter 15. Then I'll have the office hours now. Then Felipe will have office hours. And then on Sunday we'll have again, okay. All right, that's it. So we'll post everything, and then I hope to see you, some of you, at the office hour, and then at the exam will be here.